Okay, now that we've gone through the examples, let's have you folks start to work on the practice questions on your own. So that would include the practice questions of this gallium metal here question, the carbonic acid and potassium hydroxide, the potassium oxalate question, and the paraffin wax question. Okay. After working through those, you can check back to our answer key videos to find the answers to these questions. Okay, this is the answer key video for those 4 practice questions. Here we go. Gallium metal reacts with a solution of calcium iodide. Okay, gallium metal, that's G, I believe Ga. Let's have a quick look. Ga plus 3. And it's a solid metal we're dealing with here because it says it's a solid metal. Solution of calcium iodide. Well, calcium is a +2 ion. This is an ionic compound. Iodide is iodine with a -1. So we need 2 of those. So let's put these together. Gallium metal reacts with calcium iodide. 2 iodines required. And it is aqueous because it says it's a solution. We do the reaction. It looks like a single replacement reaction, which is metal for metal. One metal with one ionic compound always replaces metals. So we end up with calcium as a solid metal plus gallium iodide. Now because gallium is a +3, iodine's a -1, that means we need 3 iodines there. Let's check and see if it is soluble or not. So we know it's ionic or aqueous or solid. So let's see, iodide is here. Most things are very soluble except for copper, silver, lead, mercury, and tellurium, looks like. So that'd be in the very soluble section, which means this is not a precipitate. This is aqueous. Now we have to balance it. So let's start with the iodine or the gallium. One there, one there. Calcium, we've got one there, one there. That looks good. Let's do the iodines. 2 there and 3 there. So if we put a 3 here, that'll take us up to 3 times 2 iodines is 6 iodine atoms, which means we need a 2 here because 2 times 3 is 6 iodine atoms. That makes 2 galliums, so we need 2 galliums here, 3 calciums, which means 3 calcium atoms there. Okay, now the equation's balanced. It's good to go. Let's try this question. Carbonic acid with potassium hydroxide. So potassium hydroxide, potassium is K with a +1. Hydroxide is OH -1. So that makes KOH. There's our base. We know it's a base because of the hydroxide. Now let's look at the acid. It's carbonic. Ic comes from 8 in our naming rules. So that must come from the atomic polyatomic ion of carbonate. Okay, now carbonate, let's look it up. It should be carbonate. We check our periodic table. There it is. CO3 - 2, carbonate. So we go back. CO3 - 2. That must mean that it needs 2 hydrogen ions for its, to make it into an acid. Those are the cations we use. So that would be H2CO3. Okay, so now that we've got the 2 reactants, let's lay them out. H2CO3, that's carbonic acid. It's aqueous. Plus aqueous potassium hydroxide. This looks like a pretty simple neutralization reaction, base and acid mixed together. So we've got our potassium swapping for a hydrogen. And that's going to create, of course, water, H2O, liquid. As this hydrogen comes here and replaces K, we get HOH, which is, of course, basically H2O. So that's done, plus potassium swaps for the H2. So we need 2 potassiums, of course, to go there. So we'll have 1 potassium with a charge of +1, and a second one with a charge of +1. That's 2 potassiums to balance out with the CO3 - 2. Let's check if that's a precipitate or not now. Let's see here. So we go down to, there we go, carbonate, group 1 ions. Most things are not soluble. Let's check if potassium's a group 1 ion. Let's see. Potassium, there it is, group 1. So yeah, that's going to be quite soluble. So that would be aqueous. Usually it's not. Now just the balancing. Okay, let's do some balancing in green. 2 potassiums here. If we do 1 molecule of potassium carbonate, that would mean 2 molecules of potassium hydroxide, because 2 times 1 is 2. Let's do the CO3. We've got 1 CO3 there, 1 CO3 there, so that's fine. Let's do the hydrogens. We've got 2 times 1 is 2. If we make this a 1, that means 1 molecule of 2 hydrogen atoms, or ions, that's 2 hydrogens, so that's 4 hydrogens in total, which means we need a 2 here, since 2 times 2 is 4. Okay, let's keep going. 2 times 2 is 4. Let's do the oxygens now. So we've got 3 oxygens here, plus 2 here is 5. We've got 2 here, plus 3 here is 5. So this looks good. Done. Let's try the potassium oxalate solution. So potassium oxalate and calcium chloride. Calcium is a +2, chloride is a -1. So that's a simple ionic compound, CaCl2. Of course, 2 chlorines to balance out the +2 on the calcium. Let's do potassium oxalate. Potassium is K+1. Oxalate, that's an interesting name to it. Sounds like a polyatomic, so let's check our polyatomics. Where's oxalate? Here it is. OOCCOO with a charge of -2. Oxalate. Okay, let's go back. OOCCOO with a charge of -2. So, of course, we need 2 + 1 potassiums to balance out 1 -2 oxalate. So it should look something like this. Okay, now that we've made our reactants, let's put them together. Let's check if these are aqueous or solid. Actually, it says they're aqueous here. It says solutions, so we don't really need to check. Those are going to be aqueous and aqueous. Now we should see that every time we see 2 ionic compounds reacting, that's a double replacement reaction. So calcium for potassium. Let's do a quick swap. 1 calcium is +2. Oxalate was -2. So that means we just need 1 of each. 1 calcium with 1 oxalate. And that means potassium swaps with chlorine. Potassium's a -1. Potassium's a +1. Chlorine's a -1. So that means we need 1 of each. That's good. Let's check if those are solids or aqueous. So potassium chloride. Here's chloride. Potassium's not in this column, so it's in the most. That means that this is aqueous. Quite soluble. Let's check calcium oxalate. Maybe it's on there, maybe not. Oh, there's oxalate there. That's good. So what is it soluble with? Group 1 ions, ammonium, some of these guys. Most things are insoluble. Let's check if calcium's group 1 or group 2. So we go to calcium. Looks like it's group 2. So it's almost soluble, but not quite. That means this is going to be solid. It's going to be a precipitate. Let's do balancing in green now that our formulas are nicely made. Everything's, the molecules are correctly made with ionic compounds. Let's do the chlorines. 2 chlorines here. So 2 should be here, so we got to have 2 molecules of that. 1 chlorine, or 1 calcium, 1 calcium, that's fine. 2 potassiums, 2 potassiums, that's fine. 1 oxalate with 1 oxalate, that's fine. So, what if we do a 1 to 1 to 1 to 2? Yep, that looks like it'll work out. Perfect. Let's go down and try the paraffin wax question. So paraffin wax, it's for candles, and here's the formula they're giving us. It's quite a large molecule, burned in an oxygen-rich environment. Okay, well, we know that we always take our hydrocarbon. In this case, it's a wax, so it's solid, and we burn it in oxygen gas. All fire requires oxygen gas, and those are going to react to, of course, form carbon dioxide gas and extremely hot water, which is water vapor. Those are always our products. So now we have to balance. Okay, balancing in green. So we've got 31 carbons there. Let's do 31 here, because 31 times 1 carbon is 31. Okay, so now those are balanced. Just assuming this is a 1 molecule there. Let's do the 64 hydrogens. So 1 times 64 is 64. That means we need a 32 here. 32 times 2 is 64. Now, let's check our oxygens. 32 oxygens there. 31 times 2 is 62 plus 32. That looks like 94 oxygens in total. 94 will work. It's an even number. So I think that would be 47 here. 47 times 2 is 94, I believe. So we need to use a lot of oxygen molecules to burn just 1 paraffin, but looks like that is balanced and ready to go now.